So the James Webb Space Telescope, also called the Webb Telescope, is going to be launched in about 4 years, and it will augment and eventually supplement the Hubble Space Telescope. This is going to be probably the most sophisticated piece of hardware or instrumentation that's ever been put in space. The James Webb Space Telescope is so large that it doesn't actually fit into any launch vehicle, so it has to fold up. And essentially one of the things we do here at Ball Aerospace is we're in charge of putting the thing together after launch, albeit by remote control. And we're not talking about large motions, we're talking about very small adjustments. By the time we're done, we should be able to position the mirror segments where they need to be to within a handful of nanometers. Well, it's a lot bigger than the Hubble Space Telescope. The primary mirror is 6.5 meters in diameter, whereas the Hubble Space Telescope is 2.6, I believe. It also looks at different areas of the spectrum of light. Whereas Hubble concentrates mostly on the visible, this telescope will concentrate on the infrared. Now that's important for a number of reasons. First of all, because the universe is expanding, everything that's interesting, that's far away, is moving away from us, and the light gets shifted towards the red wavelength. So if you actually want to see something that's a long ways away, and you look in the visible, you won't see anything. The real interesting stuff is happening in the infrared wavelengths. Secondly, the things that are a long ways away, the infrared light has a tendency to pass through intergalactic dust, interstellar dust more efficiently, so you can actually see things that would be otherwise obscured in the infrared. One of the things you have to do, though, when you're looking at the infrared is we all know that everything that's hot gives off light of some wavelength. Your body is giving off infrared light right now. So if the telescope were room temperature, all we would see would be light from the telescope. So this telescope is passively cooled to just 40 degrees above absolute zero. So we should be in a position to make whatever scientific discoveries are out there waiting to be made. We're talking about predicting the future, so it's anyone's guess what's really going to happen. But I suspect we're going to see basically the use of large detectors in astronomy more and more, and automatic processing of the data. No one can look at all the images that are going to come out of telescopes like LSST, for example. No one person could, but a computer can, and they can look for for example, one of the missions they're looking at is detecting near-Earth objects and cataloging them. Because that's not LSST's main mission, right? It's more about the looking for dark energy or something in the universe. To be honest, I don't know exactly what they're doing beyond that, but I know it has to do with dark energy. But certainly, if a telescope were used for looking for near-Earth objects, it almost certainly have to be an automated process. So you take an image today and you take an image tomorrow, and if anything moves, that's probably an asteroid. Many kids are interested in science, but even if a kid is not interested in science, everyone is interested in technology. Instrumentation, that's why I think what we do here at Ball Aerospace is so important, because we build instruments. If someone wanted to get into the field of optics, obviously you'd have to go to college and study. You can actually study optics, or you can study a field like I did, like the field of physics, and then you can work in the field of optics with a background in physics. Electrical engineering is good because there's a lot of overlap between electrical engineering and optical engineering.